All right, so today we're finishing up Chapter 8, and we're going to move on to Chapter 9. The homework tonight in mastering is stuff we're not even covering today. We covered that on Tuesday, so you can definitely do the homework for tonight. Then our next homework's not till after spring break. We're going to cover the end of Chapter 8. So the next homework after spring break is also over Chapter 8 material. So you will have all the knowledge by the end of today to do tonight's homework and the homework after spring break. So if you want to work ahead a little bit. All right, let me see where I'm at. Oh, and there is a chemistry seminar right after this class. So if you want to stick around and do the chemistry seminar, just write me a paragraph summary and email it to me to get credit for that. All right, so the things we left off with on the other day were, we were talking about trends of the periodic table. And so we talked about radius and how radius, I don't know where my little picture is. Here we go. Radius decreases going left to right, and it increases going top to bottom. Top to bottom because we have more electrons, left to right because the electrons get pulled in tighter. There are three other trends we're going to take a look at. One, this is the least intuitive, so we'll spend some time on talking about it, is the effective nuclear charge, which is abbreviated Z sub EFF. And so this effective nuclear charge is the, quote, positive charge felt by any single electron. So we'll walk through what I mean by positive charge felt by an electron. All right, so we talked about core electrons. All right, so if I had carbon, we'll say, that has 6 electrons, we would have 1s2, 2s2, 2p2. So which of those electrons are the core electrons? Right, this one is the core. And then what would I call these guys over here? Right, valence. So we talked about core electrons and valence electrons. These electrons that are considered core electrons are called that because they are closest to the nucleus, right? When we're thinking about spatial reasoning, right? These guys have the lowest energy level, which means they are closest in to the center. And those core electrons do something called shielding. So the electrons closest to the center, which are the core electrons, those core electrons shield the outer valence electrons from feeling the full charge of the nucleus. So you can think about it as concentric circles, right? If my nucleus is on the inside, the ring closest to that kind of prevents the outer rings from feeling the full pull of that center nucleus. So we'll take a look at an easier example other than carbon. We'll do helium. It has 2 electrons. And it also has 2 protons, right? 2 protons. What would be the electron configuration for helium? All right, 1s2. So we have 2 electrons, both in the s orbital, both at the lowest energy level, right? 1s2. So each of the 1s electrons shield each other from the full charge of the nucleus. So this effect, this shielding effect, is called the effective nuclear charge. So we can calculate approximately how much shielding each electron is giving to each other. Thinking way back to the beginning of the semester, we had the big letter Z before. What did the big letter Z tell us? Atomic number. And so the atomic number tells us what about the innards of an atom? It's the number of protons. So it's both the atomic number and number of protons. All right, so that's how much charge is on the inside, right? That's how much the nucleus has a charge. Why do I not include neutrons in my figuring out how much charge is on the inside? They don't have a charge, right? So it doesn't matter how many neutrons. They have 0 charge. So it's going to be the charge of the nucleus, the atomic number, minus this sigma, which is a shielding constant, which we would know for each different atom. I did not leave myself in the space. I want to write one more sentence underneath here. So the larger the value of this effective nuclear charge, the stronger hold of nucleus on the core electrons. Right, so if I have a larger positive charge on the center, those electrons that are closest to it are going to be pulled in more. Does that make a picture in your head? That is strong positive charge. The guys closest to it are going to be sucked in closer. So what would you imagine the radius of that would be? Small or large? So let's fill in a table and prove to ourselves what we just said in words, right? Knowing what we know. So on your next page, we have this snazzy table. You can tell I spent hours on it. Super impressive. All right, so we have 4 elements, and I filled in the first row, and we're going to fill in the rest and see if we can see a trend between Z effective and the radius. And we are going to be looking at elements going left to right. So let's make a prediction. If I'm going left to right, what do we already know about the radius? This way, so it gets bigger going down, it gets smaller going this way, right? Because we talked the other day about the guys over here have all the electrons they want, so they pull them in tight. So the radius over here is smaller than the one over here. So we would expect, if I'm going sodium, magnesium, aluminum, silicon, should the radius get bigger or smaller? We want to get bigger. It's going to get bigger. We'll look at the picture again. Where'd my picture go? Somewhere I just had it. I showed it like 2 minutes ago. Oh, here it is. All right, so we're going to decrease this way, increase that way. So we're going to be looking at these 4 elements on our table, right? So we're going to be expecting a decreasing radius with increasing Z effective. Let's see what happens. We already know it's going to be true. I'm just going to prove it. I mean, nothing unexpected should happen. Just means my math's wrong if something crazy happens. All right, so let's take a look at sodium. Sodium has an atomic number of 11, right? 11. So if it has an atomic number of 11, it has 10 core electrons, which means its Z effective is the difference between those two. It's a way of measuring how many electrons are actually affecting that pull. So the core electron number is approximately equal to sigma, right? What I just had in my calculation. I don't know what I'm doing with my pages today. Get all messed up. Okay. All right, so then let's take a look at magnesium. Magnesium is 1 over from sodium, so it has number 12. How many core electrons would magnesium then have? Still 10. So now what is the Z effective? All right, then we'll go to our, I would look this up, and the radius happens to be 160. So far so good. Z effective increases, radius decreases. All right, if aluminum is 1 more over, it's 13. How many core electrons does aluminum have? Still 10. Right? Because anything in this row is going to be valence. Anything in those rows before it are the core electrons. So then what's the Z effective for aluminum? All right, without even looking at the periodic table, what's the atomic number for silicon if it's 1 more to the right? Okay. Good guess. How many core electrons should it have? Still 10, otherwise this doesn't make a very good argument. So the Z effective is now 4. That's going to be our trend. As Z effective increases, the radius decreases. How to do the radius? Sure. All right. So if I look back at radius, I will look at, let's look at sodium versus argon. Okay. So sodium, we know its electron configuration. Okay. So I'm going to, actually, and I'll do one comparison going, we'll go down too. We'll compare. All right, so we'll look at those four. All right, these two are across from each other, and these two are in the same column, row, column. All right, so let's compare these two first that are in the same column, sodium, potassium. Which one has more electrons? Sodium, potassium. Potassium is more electrons, right? You could just count them up. More electrons. It has a new energy level also, right? So which one of these two has to be bigger? Sodium or potassium? Potassium, right? It has more energy levels, more electrons. So this from here to there. That's not spelled right. I'm gonna make that an M, N. I get distracted. Sometimes I'm watching myself write on my little computer screen and I just forget what I'm writing. All right, so down a column, the radius increases. Yeah?
I think we're just confused because we don't know how you got the numbers like 160, 143.
Yeah, I get
Oh,
I get
Like,
that.
should we just know that off the top of our head?
no, I read them off my chart. They're right here, 186, 160, 143, 118. Oh,
Will we have that on the test?
if you need to use it, I'll have to give it to you.
Okay.
Yeah. Yeah. I thought we wanted to explain it again. Okay.
When we had 10 core electrons in that row, specifically.
Oh, yeah, I can do that too. We'll look at, since I already have, so ignore this guy. We'll look at sodium, argon, we'll do aluminum. One, two. All right, so core electrons are all the electrons except the ones that have the highest energy level, right? So for sodium, what is the highest energy level? 1, 2, or 3? Right, 3 is the highest energy level. So everybody who's not in 3 are core. All right, what about aluminum? What's the highest energy level here? 3. So anybody not in the 3s are in the core. What about argon? What's the highest energy level? Still 3. So everybody not in 3 is in the core. And that happens to be, if you're in a row, they'll always have the same number of core electrons. Okay? All right. How do we feel about Z effective? Besides the fact that I apparently tricked everybody by reading some numbers off the table. My fault. I didn't mean to do that. All right, let's talk about the last two properties then. So, just about all of our elements can exist as either a cation or an anion. What charge does a cation have? Positive, right? And then what charge does our anion have? Okay, good. So that deals with the number of electrons, right? If it's positive or negative, the number of electrons has changed. And since the radius is based on number of electrons, if I take one away or I add one in, then the radius is going to change. Okay, by changing the number of electrons, the radius has to change. All right, so let's say an atom gains an electron. Is that a cation or an anion? Right? Anion. If I've added an electron, would you expect the radius to be bigger or smaller? If I put one more electron in there. Yep. So the radius increases because we've added an electron to that outer shell, right? Physically, there's more electrons, so we make the space bigger to have all of them. So then we have the opposite case, right? We could lose an electron, and that's our cation. What do we expect to happen to the radius if I've gone down in numbers of electron? It should decrease. The opposite case, yeah. So we'll take a look at some. Let's say, for example, let's look at sodium plus 1, magnesium plus 2, and aluminum plus 3. All right, we already looked at sodium on the previous sheet, wherever I just put that. Oh, there it is. Normally I have a good method to my madness up here, but today not so much. All right, so we have sodium with this electron configuration. Which electron is going to be lost to become sodium plus 1? Is it in the 1? Is it in the valence or is it in the core? Right, it's going to be in the valence. So the electron configuration for sodium plus 1 is that, right? Okay, I'll write magnesium. All right, so that's regular magnesium. What energy level will lose an electron to become magnesium plus 2? Right, the valence again, and how many does it need to lose? 2. Okay, let's look at aluminum. Am I going to lose an electron from the core or from the valence to become aluminum plus 3? Valence, how many am I going to lose? 3, so what's left? Yep, same thing again. We just kind of proved why atoms become certain charges. Again, we talked about it on Tuesday. But, right, we're going to lose the ones that are the valence to become left with the core. So I was S1, S2, S2P1, right? And we've lost all those electrons to become positively charged. So the decrease, we expect the radius to decrease. This figure is much better in your book, which I'm going to throw a pitch out there for the book. Definitely read your book. I'm going to say there's a lot of good useful stuff in here. Like all the answers to the homework are pretty much in the book. Because you may have been thinking like the other day, gosh, how would I have known that it goes 4S then 3D? Well, it turns out, let's get to the right chapter, chapter 8. This is pretty much the table they wanted you to make. So you could just fill in that table. Or you could have, let's see, where's the other? You could have done it like this, right? Where it's all filled in for you already. Or here's the entire periodic table with the electron configuration of every element. So that could have been helpful too when you were looking to do that. So I'm going to say the book is super helpful. One of the reasons I recommend you owning the book in some form. Yeah, and then here are all the radii that you'll need for the homework tonight. It's all laid out already. All right, so here's the figure we're looking at right now. I'll do it in color since I have my book with me. We're looking at sodium, magnesium, and aluminum. Right, sodium going from regular sodium to +1. The radius decreased from 186 down to 95. Magnesium and magnesium 2, 160 down to 65. Aluminum to aluminum +3, 143 down to 50. So it decreased a lot by losing 1, 2, or 3 electrons, right? So the ions that lose electrons, their radius gets much smaller. Should be fairly intuitive. So then let's look at, oh, one last thing. Let me give you a term that could be helpful. All three of these ions, right, that now have all the exact same electron configuration are called isoelectronic. Iso meaning same. They all have the electronic configuration, all the same. So I think in the homework tonight there's a question or two like, which of the following is isoelectronic with neon? So you'd write out the neon electron configuration and figure out which one of the ions has the exact same set of electrons. Which you could totally use your book because it's already in there. But you could also do it out by hand. That's also good for learning. But all right, let's do the opposite then. Let's talk about cation or anions. Let's look at which ones do I want to pick.
So that example that you just did was reaction.
Yep, these were the cations.
Okay.
Yep. Yep, which was this half of the, when you're looking at the next page, these guys. So we'll do the anions. Let's see, F minus, O2 minus, and 3 minus. All right, so we'll do regular fluorine over here, just as a reminder. All right, so if fluorine has become -1, and that's its regular electron configuration. Oh, not P6, sorry, P5. How many electrons is it going to gain to become F -1? 1. Okay, so where am I going to put that 1 electron? In the 1s, the 2s, or the 2p? Okay, 1s2, 2s2, 2p6. All right, oxygen has a configuration like that most of the time. How many electrons does it need to become 2 minus? 2. Which energy level am I going to put it in? The 1s or the 2s? Okay, then am I going to put it in the S or the P? P. All right, nitrogen is normally that. So how many electrons does nitrogen need to become 3 minus? What is it going to have? It's going to be the exact same. I can't think of any other clever way to ask this question. What would I call those 3 in relation to each other? Isoelectronic. Oh, let me try this. What about neon? If neon is right next to it, over here, it is also isoelectronic to it. All right, so then now we have our 3 ions, our fluorine, our oxygen, and our nitrogen. Right, neon's not an ion because it's not charged. What do we expect to happen to the radius going from fluorine to fluorine minus? Fluorine to fluorine minus. Get bigger, get smaller? Bigger. What about oxygen? Oxygen 2 minus. Nitrogen, nitrogen 3 minus. Bigger. Which one of these 3, which one should be the biggest? The fluorine, the oxygen, the nitrogen. The nitrogen should be the biggest because it has gained the most electrons.
So because it moved the farthest,
It gained the most. Yep. So the book only has fluorine and oxygen, but the trend is the same. Oh, I have the trend over here on the next page. Nope, just kidding. Somewhere I have it. We'll just look in the book. I don't know what's going on with me today. Normally I'm much more put together. There we go. So anions are much larger than their corresponding atoms, and we can see these got strontium and chlorine, but the trend's the same. A negatively charged ion will be much larger than their original atom. How do I feel about that? Good? Makes sense. More electrons, need more space. All right, let's see. This is related to a lot of the topics we just covered. So ionization energy. Ionization energy is the minimum amount of energy required to remove an electron from an atom. If I'm going to remove an electron, what charge will this new atom be? Positive, right? Because I've removed one, so now it's positive. So is that a cation or an anion? Right, cation. So these are making cations from neutral atoms. So looking at our periodic table, who is more likely to become a cation? My metals or my halogens? Right, the metals are more likely to lose an electron, right, to become positively charged. Comparing sodium and chlorine, this one's more likely to become positively charged. Which one is the larger radius, sodium or chlorine? Right, chlorine is the larger radius, has the most electrons. They're related. Right, metals are most likely to lose an electron. If they're most likely to lose an electron, is it... Oh, question first.
Starting from the left side of the periodic table, you said the radius is with the radii of the larger, correct?
Oh, yeah, sorry, if I lost an electron. Sorry. Yeah.
So,
No, I was talking about ions. Sorry.
What is that word? Likely to.
That's my O and my S merged.
Okay.
There we go.
Okay.
All right. Metals are more likely to lose an electron. So how much energy will it take for sodium to become sodium plus 1? Right? Not very much. It wants to be sodium plus 1. What about how much energy should it take chlorine to become chlorine plus 1? A lot, right? Chlorine doesn't want to lose an electron. So that's what this table is showing. So metals are most likely to lose an electron, so it takes very little energy to do that. Halogens do not want to lose an electron, so it takes a lot of energy to remove an electron from a halogen. So this table is showing over here, right, this is the lowest energy. It's increasing energy as we move left to right. So it takes more energy to remove that electron as I move towards the halogens and the noble gases. Then we're going to decrease our ionization energy as we go down the table. So if you think about this, right, neon only has 10 electrons. Radon has 86 electrons. So if neon loses 1, that's a large percentage, right? So 1/10 of its electrons. So it's unlikely to lose 1. Radon has 86. If it goes from 86 to 85, it doesn't really notice. It's such a small fraction of the number of electrons it has. It takes less energy to take 1. If you already have 86, you're willing to give up 1. So that's the decreasing this way. So there's an inverse relation between atomic radius and ionization energy. All right, because before we have decreasing radius this way, so that's an increasing ionization. We had increasing radius, so decreasing ionization energy. They're the opposites. So if you know one, and you know it's the opposite of the other, you know both. Okay, so that's the likelihood of an atom losing an electron. What would be the opposite of that? The property of gaining an electron, which is electron affinity, which is how easily an atom will take on another electron. All right, so looking at my table, based on what we already know about the periodic table, let's look at lithium compared to fluorine. Which one of those is more likely to become a negatively charged ion? Lithium or fluorine? Fluorine, right? Fluorine should always be the negatively charged one. Right, fluorine's more likely to become F- rather than lithium. Lithium's not likely to become negatively charged. So if we look at these values, right, ignore the fact they're negative. The negative's just from the way that they're measuring the fact that it's a loss of energy. Pretend they're absolute values. It's fine. So lithium has an absolute value of 60 compared to fluorine, which has an absolute value of 328. So the larger, we'll call it larger negative value, is more likely to gain an electron. So the trend increases going left to right, which makes sense, right? Fluorine wants to be -1, chlorine wants to be -1, bromine wants to be -1. these elements over here don't want to lose an electron, or don't want to gain an electron, they want to lose an electron. And so, going this way, we see an increasing electron affinity going left to right. And this is kind of funky. We'll see that it also increases this way. And it comes from the fact that, right, fluorine has only, what, 9 electrons. So if it gains 1, it has a full set. If we move down here, the bromine has 35 electrons. So really adding 1 more to make a full set is great, but it's not as critical as it would be for elements like fluorine, where they only have 9 to work with. How do you feel about those trends? For the most part, right, you can kind of think through things you already know about the periodic table and then add them to radiuses and ions and things like that. All right, let's do one thing in chapter 9, and then I'll make sure we have plenty of time to do this quiz. We'll definitely end early today. Oh, is there another slide? What's the next slide? Let's see. I may or may not have it. Let's see. Electronegativity. Oh, there it is. We'll need this. Sorry. One more thing. So electronegativity is the atom's ability to attract electrons to itself in a bond. I'm only going to touch on it a little bit now, and we're going to talk about when we do bonding. Why is it such a critical thing? So electronegativity is directly related to what we just did with electron affinity. So when we have electron affinity, right, fluorine on your whole table has one of the highest values of electron affinity. It really desires that extra electron. So again, fluorine's going to be the most electronegative. It really, really, really is going to pull the electron to it so that it has a full set. Because it only has 9. It really wants 10. So again, electronegativity is going to increase going left to right. Right, as we move from our metals to our halogens, those metals don't want another electron. They're willing to give theirs up. Where we move over to the right, where we have like chlorine and bromine, those guys are really, really want the electron. So we're going to increase left to right. And it's going to decrease going top to bottom. So this corner of the periodic table is going to, which is fluorine, has the highest electronegativity. As you go down the row, there's so many electrons in all those outer shells that it doesn't really matter much if it gets 1 more or not. If you already have 85, 86, not that big of a deal. It's a bigger deal when you're a small element. So we'll use that a lot in whatever chapter's next, 9. When we talk about bonding. All right, so let's do 1 or 2 things looking at how many people have done Lewis dot structures before? A few? Okay. Yeah, where we can have it. Not that big of a deal. always work for my notes. Pretend that these were slides. They have titles across the top. Chapter 9. 1. Lewis dot structures. About 2 minutes when I go to dig up something else. I'll find them. They're in there. All right, so right, an atom has two different types of electrons. It has valence and core electrons. Electrons in the valence shell are the electrons that are going to participate in bonding. So if that's true, why do noble gases not do anything? Why are they not reactive? Their outer shells are full, right? So they don't really need to do any chemistry. And so let's take, for example, we'll do neon. What would be the valence shell of neon, the 1 or the 2 energy level? 2. How many electrons are in my energy level 2? Okay, let's take a look at, we'll do argon. Okay, looking at this, which energy level is my valence energy level? Okay, if it's 3, how many electrons are in my valence shell for that guy? 8. What is the one thing you always remember about Lewis dot structures for those of you who have done it? You always want to get to 8 electrons. This is why. The outer valence shell of pretty much every atom wants to have 8 electrons. So we're going to try and pair up atoms in a way so that they both get 8 electrons in their outer shell. 8 is the magic number in here. So bonding is a way for atoms to have 8 electrons in their valence shell. So let's take a look at, we'll do fluorine. Fluorine's a good one, good little warm up. Okay, if that's fluorine, 1s2, 2s2, 2p5, how many electrons are in its valence shell? 7, right? 7 electrons. So if I want to draw this in a visual way, right, there are 7 little dots around my fluorine. Why do I not include the core electrons? Because they're not participating in the bond, right? They're in the core, they can't really do any chemistry. So I'm only ever going to show the ones that are in the valence. So just because I'm not showing the fact that fluorine has actually 9 electrons, it does, it has 9. I'm just showing the ones that are able to do chemistry. So if I want fluorine to have 8 electrons around itself, how many more electrons does it need? Right, it needs 1 more. What if I did something crazy like this? I'll redraw it. What if I paired it with another fluorine? Alright, so now I have 2 fluorines, each with 7 electrons. Now, each fluorine has 8 electrons in its immediate vicinity. All right, each has 8. It's sharing how many? Right? Sharing. What do we call it when it shares? We just made a bond. Right, so wherever we're going to share electrons so everybody gets to 8, that's where a bond's going to form. Okay. Let's talk about bonds and lone pairs.
So if you were to draw fluorine just as is with 7 electrons, does it matter where you get out the dot?
No. We're going to use Hund's rule, though, to kind of fill them up. So if I had nitrogen, which has 5 valence electrons, you go around one time, that's 4. Nitrogen has 5 total. Doesn't matter where I put the 5th one, it's just, right, Hund's rule says, that's good, this is, that would be not so good. Oh, 4. They each want to have their own space before they get paired up. So as you're working through how to do that. Okay, this will be the last thing we talk about today. Covalent bonds and lone pairs. Oh, let me just, that's bad. All right, so just like we said 2 seconds ago, covalent bond is a pair of electrons shared between two atoms. And if we're not using the electron bond, we're going to use one pair. And if the unchained is not paired, it doesn't belong to one. This will identify the bonds and where the other. How many does it have? How do you know two students? If they're paired between 2 different things. Bonds. This. Also, 2 electrons belong to exchange. So another to work on. This is more familiar with normally like this in the electron. So once 2 electrons here and there. If I have two employees molecule. One, right? Sorry. Who alone pay is alone pay. We'll stop when you hold and just pretty Nancy is just table here. There. You can see it. And start